Alright, part two of the greatest mistake in science ever. Kind of the Einstein mistake of creating a non-explanation as an explanation for something physical, a non-physical explanation. One containing no source of energy, just sort of a magical system where things just do something because geometry says so. Something like that. So anyway, I'm going to read from the gravitation page at Wikipedia and just do my commentary on how this isn't really an explanation or description of anything physical, or something that should be called physics as a study. Some kind of metaphysics. Anyway, gravity or gravitation is a natural phenomenon as opposed to, yes, kind of a, shouldn't even have to say that shouldn't have to say that, by which all things, that's dangerous, with mass are brought towards, or gravitate towards one another, including planets, stars, galaxy, and other physical objects. So yes, a lot of things have mass besides those galactic things, and but it gets a little tricky because they have their substance in different forms. I would argue that the real distinction that should have been made was between forces and material bits, in the sense of things that are affected by forces and things that are forces. That separation creates a pleasant continuity in that none of the forces interact with forces, meaning you can't bend light with magnetism, for example. You can't use a force to manipulate a force. You have to use a piece of a material bit as a conduit. So the argument would be is the material bits are moved by forces, and forces dictate where they go. So if an electron goes somewhere, it goes there because forces are pushing it there. And in that context, because matter is made out of those little bits, and all the little bits need to be pushed wherever they go. They can't just go. Then matter has to have a force that moves it. And gravity is not a force, technically. And therefore, I think their description of the force of gravity is wrong, because they made it a non-force as the cause of movement. And we sort of know in our real world experience that this pen, for example, isn't going to do anything at all unless somebody provokes it to. And the only circumstance that is different is that just by bringing these two things together, there's some gravity magic that happens that doesn't require any exchange of energy. Just happens. Alright, so anyway, towards one another, including planets, okay, galaxies, and other objects. I think they should have, obviously I think they could have said that better. Since energy and mass are equivalent, so because there's an equation that says E equals mc squared, they've now declared this some kind of truth, that you can convert actual matter into energy in the real, in some sort of real sense. That, but because it's capable of trapping energy or absorbing energy or containing in its formation energy holding the bits together, that the bits themselves can be broken. And I would argue that's debatable. Debatable in the sense that you can break them into maybe smaller elemental bits, like a quark, but that you can't perhaps ever break the quarks. They really don't have any evidence of that yet anyway. All forms of energy, including light. So at least they have that correct, that at least light now is a form of energy. It's a force. And but the idea of calling mass and energy the same thing, the fact that you can equate the destruction of matter into the release of the destruction of the arrangement of matter into the release of energy should not equate to that you actually converted all of the material bits into energy. You released the bonding elements, not necessarily, you released the glue, not necessarily did you convert the actual material bits, which have no force without force pushing them, so they have no energy. So in a sense they have no mass. So that's the trick of it. You can almost think that mass is a symptom of having momentum, and photons definitely have that, where I could argue a material bit, like an electron, that has no momentum, that is, it's not moving at all in any frame, would have no mass. Because without momentum it has no mass. Anyway, causes gravitation and are under the influence of it. Okay, all forms of energy, including light, cause gravitation and are under the influence of it. So, in a sense, they took light, called it energy, and then said energy makes gravity. And there's no evidence that, say for example, the virtual photons that they imagine to exist that convey the force of magnetism, they don't think those create gravity. They don't think something, well, I guess they might, but you know, there's no hard evidence that this is true. Anyway, and it just breaks the understanding that the force elements create gravity. They're what makes gravity. They're the cause of the force of gravity. Their existence creates gravity. They don't have gravity. They don't display a symptom. They are the disease of gravity. On Earth, gravity gives weight to physical objects. It's kind of simplistic, and causes ocean tides. And that's kind of a simplistic statement also, but whatever. Doesn't really get to the subject, and especially without pointing out that it's the moon that causes the tides. The gravitational attraction of the original gaseous matter present in the universe. So now they're going to speculate about what they think the causes of the universe are. So they're not going to just explain gravity here. They're going to tell us that they have some sort of knowledge of what the universe was originally, and kind of just proclaim it as this is the part of our context of the description of gravity is your acceptance of some theory of creation. Caused it to begin coalescing, forming stars. I would argue that when you get to the small particle dynamics of the universe, gas clouds and whatnot, that it's more likely that gravity is not the significant player, that charge is. Static charge, like I could rub a balloon on my shirt and it'll stick to my hair, kind of thing. That force transfers very far. If you think about how far this little tiny electron is creating a force that's pulling or creating a bond between another substance that compared to the electron is very, very far away, and yet it's a strong enough force to pull things together. So I think it's likely, it's all the same force. I mean, the bottom line is it's all, by my theory, it's all the same force. So making these distinctions between whether it's a symptom of magnetism or a symptom of gravity, it's all the same elemental bits that are creating the movement. But it's a better understanding to understand the difference of the manifestation of the force. Photons are little bits at a frequency. Magnetons are ones segregated through polarization. So there's two kinds of this fundamental quantum energy, and when they're separated, they can have more effect. the effect can be magnified. And magnify. Coincidental, good idea in terms of a way of describing something. Magnets are really just a magnification of gravity. And then you have gravity, which is the loosest form. It's just polarization and momentum randomized and without a frequency. Alright, so back to the story. Where was I? Group together, okay, forming stars, and for the stars to group together into galaxies. So galaxy is so gravity is responsible for many of the large-scale structures in the universe. So again, those are all their assumptions or proclamations, some very poorly evidenced, I would argue, and really shouldn't be part of a declaration of a truth. They should at least say most scientists believe or something. So gravity is responsible for many of the large-scale structures in the universe. Gravity has an infinite range, although its effects become increasingly weaker on further objects. I mean, I'm not going to disagree that the potential of an infinite range can be stated, but in a sense, in terms of laws of probability, that infinite range has no meaning, because you could argue that something could exist in something's gravity and never be influenced for tens of thousands of years by a single element of that gravitational influence, and that its influence would only be felt one moment every 10,000 years. So it's kind of hard to call that a real phenomenon, in the sense that, you know, if the period becomes so long, it's, you know, hard to call it a real influence. But anyway, technically correct, but infinite just is a, you know, that is an awful long time, and you could spend a half an infinity waiting. And if you're going to spend a half of an infinity waiting for something, I don't think you'd call that a meaningful event. Gravity is most accurately described by the general theory of relativity, proposed by Albert Einstein in 1915. So, you know, it has some advantages in the sense that it describes, it doesn't describe, it is a description that has some points in its favor in terms of it being a good theory of gravity. But those points are rather small when looked at in detail, in terms of their minor consistencies with minor elements of the truth, and they don't get to they provide more problems than solutions. The minor advantage of Einstein's theory, adding more accuracy in terms of recognizing that the sun is not a stationary object, and that it processes in its orbit, and that precession causes Mercury to precess. That's a good, valid thing, but the price for this is this notion that a non-force is creating or generating the energy for gravity, and that, in my opinion, is a huge mistake. Alright, which describes gravity not as a force. Okay, so Einstein is, they say, he's saying it's not a force, whatever, but as a consequence of the curvature of space-time, which you could just describe as a way of describing the symptoms of gravity. You could say that the symptoms of gravity are like, and so space-time can be a metaphor for what the symptoms are like. Now I would say the time element is just bogus, because time isn't a dimension, it's a function, and it can't be bent in any way. But let's just say the curvature of space in terms of the gravity part of the relativity theory is just a simple diagram of a convergence. It's just basically telling you that things move towards a center. And you know, like putting a weight in a fabric, and this fabric's under tension and it moves evenly to represent the mass, or the fact that you're bending something. So it's just a metaphor. It's just an analogy to what gravity looks like in terms of how it can affect things. And it shouldn't be assumed that because the analogy does the simple thing of duplicating the function, that that's the answer, because that function can be duplicated with many other mechanisms. So very quickly I'll give you my mechanism, which is this field. We're all just sitting in a huge field of energy. So these are all little photons moving the speed of light in all directions, and they come in two polarizations. And so just for illustration, red and black. And they fill all space evenly and completely, in the beginning anyway. They cause everything else that happens, essentially. They're the things moving. And anything that's moving, anything human or anything in the world that moves because of how it's releasing, trapping and releasing those elements of force, because they're what moves electrons and protons around. But the consequence of this field of energy that has no frequency, so none of these are coming at a constant frequency, and none of the polarization has been filtered. So there's no mechanism in that diagram, like a magnet, where the force would come in and it would leave filtered. That is, all the red would go this way and all the blacks would go another way, something like that. So the consequence of this is that every thing in the universe that's a thing, so no matter how small or big you make the object you call a thing, so whether you go into the deeper space, there is empty space. There's space as black as the space in the sky inside of me. And each one of the little bits that make me up, each clump is in that space, in a sense, in that atmosphere. And each thing is going to be doing this in that field. It's going to be getting hit by pieces of that energy. And as long as the field is balanced, that is randomized, everything's going to be equal. So it's going to be hit by as many arrows going this way, as many this way, as this way. And so its vacuum state is just to be neutral and to be in one place. But it's going to seem from its perspective that the universe is constantly hitting it with this pressure. A constant pressure from all directions. Constant bombard by this field energy. And it all, even though the thing came from billions of light years away, just like a photon from a galaxy when you look in the sky, that photon hits you. It traveled all the way across the universe and hit you. It's always personal. So, and so the consequence of that center of gravity, that's essentially this is why gravity creates spheres. Is because this pressure is constant and even, and it will force things to become round. So the consequence of that mechanism, that we're all just surrounded by a field of even bombardment, is that what's hitting me can be interrupted if something else gets into the field with me. And this other thing will block the stuff going from this direction. And then I'll have an unevenness. I won't be even anymore. So if something enters here, it will block the stuff going this way. And so I'll have low pressure here and high pressure here, and I'll move this way. So that's sort of better illustrated here, I believe. Hope you can see this. But the point being that you have to think of the energy going into the object and staying there. So it doesn't go here. So these little red arrows over here, they would be going the speed of light and hit here. But instead they're going to get stuck in here. And instead of this thing going the speed of light, this whole big thing, it's going to go a tiny percentage of the speed of light, because this is only one little blob. And likewise over here the same thing is going to happen. And so we have low pressure between the two. This, the stuff going this way doesn't get to this, so this feels more pressure coming this way and it moves this way. And they too just keep doing that. So a way to illustrate that would be to think of a giant blob of, say, silly putty in space. So I have a 500-pound blob of silly putty, and I have another 1-ounce piece of silly putty, and I throw it at the blob of silly putty. Now the little piece I throw, say, is going 50 miles an hour, and it hits the big blob and sticks to it. Well, what's the big blob going to do? It's not going to go 50 miles an hour. No, it's going to go the percentage of the weight. So you got to do 16 ounces times 500 pounds. It's going to go 1/100,000th of the speed that the thing I threw it at was. So whatever 1/100,000th of 50 miles an hour is, that's how much the big blob is going to move. So the movement of the Earth towards the Sun is, the two bodies are moving towards each other actually, but they're only in mass terms. But you have to think of it in terms of the Earth has absorbed a bunch of energy moving the speed of light, and it's converting it into movement much slower than the speed of light. So it can collect a whole bunch of energy going the speed of light because it's so massive. And it'll return that energy when it finally collides with something, because it has this thing called momentum, which is just the storage of all of those photons that hit it. So let's say if the Earth wasn't rotating around the Sun and we put the two things in space, and let's say it takes 1 day from where we placed it for it to fall into the Sun. Over that period of the day, all the energy that hit the Earth and pushed it, nudged it, kept nudging it towards the Sun. When the Earth finally gets to the Sun, it will release all of the photons it absorbed in the process of falling towards the Sun. So anyway, that's traditionally this is described as a Lagrangian type theory. The particle gravity, though, was first proposed by a French person some 300 years ago, and it creates some problems. Like all theories, they have to work out what the consequences of it are. But I have worked out those consequences and provided suitable explanation for how they're not a problem, these thermodynamic problems that might be created. But the real point is this model completely duplicates Einstein's bent space. The mathematics that it creates are exactly the same. The inverse square law is exactly duplicated, just as Einstein's bent space is. So clearly there's other models that can explain the phenomena that exists, and we don't, science shouldn't have leaped to the first model that did a decent job. And clearly Einstein's model did a decent job of satisfying the conditions, necessary conditions, but it also created a horrible burden in terms of creating a consequence, that is movement without energy, movement without a force that instigates it, which many scientists should have found just as onerous a liability as the liability of particle theories that create a field through which objects have to be able to navigate through, a force that can create a negative friction, again, that has to be accounted for in some way. With the Einstein theory, there was no obligation for Einstein to account for the negative consequence of movement without a force. All right, probably enough. Okay. Alright, gravity is most accurately described by the general theory of relativity proposed by Einstein, which describes gravity not as a force but as a consequence of the curvature of space-time caused by the uneven distribution of mass. Now, I don't understand what exactly that means, the uneven distribution of mass. The fact that mass is distributed, how evenly it's distributed, I don't think we can know that. But anyway, I don't think they needed this uneven distribution thing. Anyway, the most extreme example of this curvature of space-time is a black hole. Now, why they went there, I mean, they should have just dealt with the gravity that we're sure of. And they shouldn't be jumping to define objects that we don't have any certainty of, especially as they're described. That is, black holes with solar masses of 2 million and something. The fact that there may be dark objects that have extreme mass may be true, but whether they're black holes, that is, highly condensed material bodies, is it's a different question. The most extreme example of this curvature of space-time is a black hole, from which nothing can escape once past its event horizon, not even light. So again, this argument that somehow light is affected by gravity, and even to the extent that they would argue some that light can't somehow overcome gravity inside of a black hole to free itself from it, but somehow the gravity is moving faster in the opposite direction, when light's not supposed to be slowed down by such encumbrances. The problem is they believe light can be bent, so the problem is the light can always, any line off the perfectly perpendicular would have a tilt to it, and that tilt would mean that it would constantly keep bending it down, so that would create a curve that would end up with a collision eventually. But anyway, this shouldn't be in the gravity page. From which nothing can escape once past its event horizon, not even light. I mean, this is all just stuff speculated to exist. No evidence that black holes exist or that their event horizon exists, and no hard evidence really that light has any problem navigating through gravity. However, for most applications, gravity is well approximated by Newton's law of universal gravitation. And there's nothing about Newton that is in any way a description of how gravity works. It's just a description of the symptoms of gravity. It's just telling you, explicitly in a formula, the relationships that exist between mass and distance, and how those are reliable symptoms of gravity. But it gives you no mechanism. Again, there's nothing to explain where the energy comes from to cause things to move. Which describes gravity as a force, at least he calls it a force, which causes any two bodies to be attracted to each other with the force proportional to the product of their masses and inversely proportional to the square of the distance between them. So that part's just totally unnecessary, because all his equation really does is just equate the mass and distance, and just say that the strength of gravity is completely dependent on the fact that if you increase the distance, okay, and the same mass, you'll get a lower number. So that the distance is in the numerator, and the mass is the denominator. So if you make the mass bigger, you get a bigger number. You make the distance bigger, you get a smaller number. That's the inverse relationship. But that's all there really is a recognition that there's two factors that affect gravity. That is, how much density, mass, and how far. Density is really what the whole equation equals. Distance and mass is essentially saying the same thing as I have 10 things in this much space and I have 10 things in this much space. Obviously, I'm less likely to hit a thing if it's in this much space. The smaller space I can confine it to, the more likely it is a line is going to hit something. And so that's just pointing out that relationship, and that's a spherical relationship, so that's why it becomes the inverse square law. Half the distance, twice the distance, 4 times the force. It has to do with the relationship between the circumference of a circle and its diameter. Alright, so gravity is the weakest of the 4 fundamental forces of physics. So this again is sort of a mistake. Now, by Einstein's theory, they claim it's not a force, and now they just called it a force. Put it in the category of a force, even though they say it's not a force. So I'd say points off for that inconsistency right there. But the idea that you can compare forces on scales of the universe that are so very different, the electron scale, an apple is to the earth what an atom is to an apple. So atoms are even incredibly tiny things. The nuclear bits inside of them are even more, another step, another earth to apple relationship. So it's kind of silly to talk about the strength of forces affecting things that are on such different scales. But gravity is the only, in a sense, gravity is the first force. It's what all the other forces are just a manifestation. So photons, the whole electromagnetic spectrum, infrared, X-rays, all that stuff, is just a symptom of when you take some of this gravity stuff and you shoot it at a frequency. And magnetism is just segregating the polarization. So it's all the same force. The other variations have more effect on particular elements. So we understand that there's a strong relationship between shooting this gravity at a frequency, that is, stuff coming at a frequency, and its ability to affect electrons. So electrons are highly sensitive to frequency. Specific wavelengths of light will affect substances very differently because they're selective. And so we think it's a stronger thing because of how much there's an effect. But the effect is only a symptom of the fact that the frequency or resonance of the photon happens to be the weak resonant frequency of the electron. But no reason to think the force is innately stronger, or that it's more, or it has anything called more energy. Frequency isn't equal to energy. Alright, it only means that if you can shoot more bullets if you shoot the bullets faster. It doesn't make the bullets any stronger. It just means you can shoot more in a specific amount of time if you shoot them faster. Alright, approximately 10 to the 38 times weaker than the strong force, 10 to the 36 times weaker than the electromagnetic force, and 10 to the 29 times weaker than the weak force. So again, these numbers are just essentially close to the very number that is the difference between the apple and the earth. So this is just a symptom of the fact that they're measuring the force. You can't use the same ruler to measure the electron as you do to measure the apple. Anyway, as a consequence, it has no significant influence at the level of the subatomic particles. Again, even that is just such an understatement in the sense that I could walk 500 miles away from a light bulb, and we could argue that only one photon, per 10 minutes from that light bulb will hit my eye. But the fact is, when it hits my eye, it's going to do exactly something just as strong as when I'm close to it, to the individual electron that gets hit by the photon. To that electron, there ain't going to be no weak force. It's plenty strong force. It's a real photon. It's a real bullet. So I guess that would be a good analogy. If light bulbs were shooting bullets, okay, yes, I'll get hit by more of them when I'm close, and fewer of them when I'm far away. But the individual bullets are not stronger and weaker. The bullet that hits me when I'm standing 500 feet away is going to be just as lethal as the bullet that hit me when I was 5 inches away. So I think it's just a very sloppy way of describing the actual thermodynamic significance of the force. As a consequence, it is, in contrast, it is the dominant force in the macroscopic scale, and is the cause of the formation, shape, and trajectory orbit of astronomical bodies. I'm glad they put the word shape in there. Yes, it causes things to go round. For example, gravity causes the Earth and other planets to orbit the Sun. Well, it sustains them in an orbit. I mean, the real cause of the orbit is their velocity. Without that, they would fall into the Sun. It also causes the Moon to orbit the Earth and causes the formation of tides, the formation and evolution of the solar system, stars, and galaxies. I don't think they've answered all those questions. So again, yes, I would say it's likely gravity's the main player, but you can't exclude things like magnetism from playing roles in those formations of things that are formed out of gas to start with. The earliest instance of gravity in the universe, possibly in the form of quantum gravity, now this they should never put in here, possibly in the form of quantum gravity, supergravity, or a gravitational singularity along the ordinary space and time developed during the Planck epoch. So they're talking about milliseconds into the birth of the universe. This is all complete speculation. I mean, just almost nothing to give them any indication that there's any kind of right or wrong answer, and yet they put this in a description of gravity. Why? I mean, it just has nothing to do with any hard science at all. Possibly from a proverbial primal state, such as false vacuum, quantum vacuum, and virtual particle. I mean, none of these things even have descriptions. Virtual particle is just a placeholder. Why would you talk about something that's just a placeholder? You're clueless. It's called the clueless particle. Clueless. We don't have an explanation, so we just invented the clueless particle to take the place of anything to explain how something got from here to there. It's invisible man particle. I mean, it's just complete made up placeholder nonsense, and here they are talking as if this has some like this should be as if this should be as common as your understanding of Saturn, moving around the sun, that this is somehow as reliable as that, and it's not. In a currently unknown manner. Well, the whole thing you just said is currently undeveloped. It's not even a glimmer in some papa's eye yet. I mean, it's not even a fertilized egg. Attempts to develop a theory of gravity consistent with quantum mechanics and a quantum gravity theory, which will allow gravity to be united in a common mathematical framework, a theory of everything, with the other three forces of physics, are a current area of research. Daydreaming. And fundamentally, as I'm going to argue, that can never happen, because the two systems are both wrongly focused. And one system clearly is more, you could argue that the foundations of quantum mechanics was quantizing a particle. That is, it was taking a discrete substance in the universe that causes effects. that discrete model isn't going to work with bent space, because it's recognizing the forces that move things. It's accounting for force. It's saying you have to have force in to have movement out. So it's not going to provide any much room for invented things, unless you want to just call gravity particle virtual particles, where I'm arguing you might as well call them real particles. Second, then the quantum mechanics became wave theory, which is essentially a kind of ether theory where everything's a field. So now they've created the electric field, the magnetic field. They have every particle, the 100 or so particles they've found, they've given a specific field to, the Higgs field. So, it's not going to be compatible with field making. So they're not going to be able to unify. And it's just that Einstein's theory is not correct. It's just, bent space, like I said, is a nice metaphor, but it just doesn't mean anything. It's describing symptoms. It isn't describing the mechanism of cause at all. It's not even coming close to a causal event that makes something move. And quantum mechanics is all about tracing cause, and about determinism, and about accountability for how something happens. But yes, Einstein's is just wrong. It's a nice little model, but it's not accurate. It's not the way it works. It's not a bent fabric. It's not a magical convergence. It's an actual force made of actual, definable, quantizable energy. Alright, so I don't know if I want to do the, I can say earlier concepts of gravity, so they gave it a whole 2 sentences. 2 sentences to the thoughts of mankind over time regarding what causes things that go up to come down. And they gave it 2 sentences. Let me read it. Early concepts of gravity. While the modern European thinkers are credited, so they even have to throw in racism, super, are credited with the development of gravitational theory, there were pre-existing ideas which had identified the force of gravity. Some of the earliest descriptions came from early mathematician astronomers such as, I don't know, some guy, Ira Baba Hababa, who had identified the force of gravity to explain why objects do not fall out when the Earth rotates. Later, the works of refer to the presence of this force. It's kind of sad that, somehow people get referenced, and other people just never will be, who did the real work. It's like the Lesage gravity thing. Lesage just took another guy's, the dead guy's, notes and resold it. And, why should the gravity be known for the guy who just stole it, essentially? He was a nice admirer of the guy. I'm not saying he meant to slight him, but the truth is, he's not the guy who thought it up. There's lots of unfairnesses in the universe, and Wikipedia sort of just demonstrates them. They ought to just call it Unfairnipedia. This was a major departure from Aristotle's belief in heavier objects have higher gravitational acceleration. Galileo postulated air resistance as the reason that objects with less mass may fall slower in the atmosphere. Galileo's work set the stage for the formation of Newton's theory of gravity. Yeah, well, I don't know. Clearly understanding that concept had to be done eventually. So it's when are they going to figure out that, yes, the atmosphere is affecting how fast everything happens, and things would happen faster. Baseballs would go forever and all that kind of stuff without the interference of the atmosphere. So Newton's theory of gravitation. We'll read the first. So that was all they gave to the scientific revolution. Here we go. So just 3 sentences on the history of theories of gravity. No mention of Lesage, of course. Modern work on gravitational theory began with the work of Galileo Galilei in the late 16th century and early 17th centuries. His famous, though possibly apocryphal, experiment dropping balls off the Tower of Pisa, so they say it may never have happened, and later with careful measurements of balls rolling down inclines. Galilei showed that gravitational acceleration is the same for all objects, so it's really just, they should have just said Galileo instead of scientific revolution. This was a major departure from Aristotle's belief that objects have higher gravitational. Oh, okay. Somewhere I don't know what I did, but anyway, I've already read that part, so I won't do it again. Yeah, so they're just giving the credit to. So the scientific revolution is Galileo, and then they go on to Newton, and that's it for a discussion about, you know, I mean, the most tangible, everywhere kind of force. I mean, nothing can really escape the influence of it, and you know, this is how much they give to the you know, understanding the symptoms and diagnosing the disease, the cause. And they're just so certain that what they've got is the truth that they've just thrown out any idea of speculating about anything else perhaps being the mechanism. And it's just a complete confirmation bias thing. Alright, so we'll deal with this first paragraph of Newton. In 1687, amazing, English mathematician Sir Isaac Newton published Principia, which hypothesizes the inverse square law of universal gravitation. So again, it's this idea of just recognizing that gravity is a center, and that as you expand the center, the circumference expands 4 times, at 4 times the rate that the distance does. In his own words, I deduce that the forces which keep the planets in their orbs must be reciprocally as to the squares of their distance from the centers about which they revolve. So just a fancier way of saying it's spherical, and again, if I have 10 bullets being shot out of a center, the further and further away I go from that center, the less and less I'm going to likely get hit by a bullet. And the same probability, you know, like you can imagine if there's a gun that just shoots in random directions, and you're 5 feet away, and then you're 50 feet away, you can understand that you might even be able to eat your lunch in peace 50 feet away, because you know the odds of just 10 bullets, very, very small odds you're going to get hit 50 feet away. But at 5 feet, you're going to have to worry. Alright, because you'll take up a bigger, your shadow, the amount of the pi of the circle is bigger. So if my hand is in this circle, and then I put my hand in a circle that's this big, the percentage of the circle that my hand is, well, I should use my finger, and then I can do a much smaller circle. The percentage of the circle that my finger is so much smaller, and I only double the distance. That's the inverse square law. Now, that's not earth-shaking. It's not something that, obviously, I don't think it's the kind of thing you could say we wouldn't have figured out pretty quick, because, yeah, that's kind of just fundamental. I mean, it's kind of obvious in hindsight, so it's not the kind of stuff that is highly technical or in any way obscured. It's right there to be seen, but yeah, yes, you have to have the instrumentality to see it. And so it was about time almost that Newton would observe that truth. Yeah. Alright, well, anyway, that's probably enough. I guess there was one person asked a question about, I think he has a confusion about rotation, so I might as well throw it in here real quick. When you do part 2 to this video, would you mind going into a bit more detail about how the Earth's rotation is affecting its gravitational relationship to the Sun? Well, the Earth's spinning doesn't have anything to do with anything. I was talking about the orbit of the Earth. But all rotation has to be understood as just vectors in a direction. So when something's spinning, okay, we'll just draw a quick picture. You just have to kind of understand that it takes and it gives back everything it gives, right? So the rotation is always opposite. So if it moved this way, later on it's going to move that way. And if it moves this way, later on it's going to move that way. So it's all about just even, balance. Is what it tends to be created out of. And it's just a maintenance of that balance. So, but I don't think there's much to say about it having any real meaning in terms of gravity. The meaning in terms of the Earth's orbit, the argument I was making, is that as the Earth orbits, even in its ellipse, because it moves faster and slower and cuts the same amount of space and all that kind of stuff, the point is it spends as much time pulling the Sun this way as it pulls the Sun that way, and that way, and that way. So in the end, the Sun doesn't get moved anywhere because the Earth pulls it in every direction as it goes around the Sun. So in the end, the Sun ends up back where it started. But the Sun does actually move towards the Earth in the process of creating gravity. Okay. So, I think that's enough. And so I'll probably might do a part 3, or anyway, I just this is just working on trying to formalize a way of presenting this information in a manner that can be understood and appreciated for the fact that it looks so much like the truth to me, like the right answer, because it doesn't create any conflicts. It's simple, it's not made of any invisible things or dark things or nothing contrived, and it's just so basic. Just polarization and the force carrier just being stuff moving the speed of light, little bits moving the speed of light that interact in a specific way with electrons and protons based on polarization. And it answers all the questions, all the ones that need to be asked.